In this video, we're going to use some calculus to help us find the work done in a system. And so you may have seen work before, calculated work before, but probably with more simplistic equations where the force was staying constant. So let's start by defining how we calculate work. We calculate work as the force times the distance over which the force is applied. So work is equal to F times d, where F is in terms of F is the force, d is the distance. The SI unit for force is Newton, and the distance is meter. So if we think about multiplying force times distance, we would get newtons times meters, or Newton meters. And you will hear it said like that on occasion, but Newton meters is very cumbersome, and force is just such a common calculation that it gets renamed as joules. Joule, a major contributor to finding work. So we will be using this joule notation, or J, but keep in mind it is just the same as Newton meters. All right, so this is a relatively simple calculation if we have a constant force. So for instance, if I state just very simply force is equal to, let's say, 5 newtons, and the distance applied is equal to 2 meters, well then our work would be equal to 5 times 2, or 10 joules, and that would be very simple. But what we want to do now is say, well, what if the amount of force is changing? Because that is very commonly the case. The force applied is not the same because the system is changing. Inherently, as we pull things up or let things down, or as the problem is changing, there's weight change. Just think about pulling up a rope. The more rope you pull up, the less force you have to use because there's less rope hanging. You have less weight actually hanging down. So systems tend to change, or the forces tend to change within those systems. So we can calculate work done by a variable force f of x from x is equal to a to x is equal to b, as w is equal to the integral from a to b f of x dx. So let's start with an example with a variable force. So let's say you're pulling up a bucket of water. That initially weighed let's say 150 pounds. Let me change this just so we have, yeah, that's fine, we'll leave that, 150 pounds. Halfway up, half the water is gone. Assume that the bucket is leaking at a constant rate and neglect the weight of the bucket. So the bucket would have some weight. We wouldn't ignore that aspect of it for right now. It just makes the problem a little bit more simple, so we'll concentrate just on the water within the bucket. So bucket of water, the water essentially weighing 150 pounds, ignoring the bucket altogether. If you need to pull the bucket up a distance of 20 meters, how much work is done? All right, so we need to start here by thinking about the force equation. So obviously 150, we're also going to, I should ignore the weight of the line or whatever we're pulling it up with, the rope. So just kind of concentrate on the bucket for this instant in time. So we need an equation for force. And had we just been, say, carrying this 150-pound bucket, quite a big bucket of water, right? But if we'd just been carrying this around, it would have just stayed the same. It would have been the same. So if we just continually lift that, say with a helicopter, and we're just lifting it higher and higher into the air, we just take 150, we'd multiply it by the 20. But we're told that this is a leaking bucket. And so what we need to do is we need to figure out what this force is based on how it's changing. So the force would have been 150, except we're losing some. And so what we need to figure out is what that slope is, what that rate of loss is. So let's do that over here, the slope. We know that we have 150 initially. We're told that it is half. Let's see where that is. Assuming the bucket is leaking at a constant rate, halfway up, half the water is gone. And so that means half of 150 would be 75. And that's halfway up, so that would mean that that would be at a height of 10. So at a height of 10 meters above the ground, 75 pounds are in the bucket. When we started out at position 0, 150 pounds were in the bucket. And so when we simplify this, we'd have negative 75 over 10, which means we are losing water at a rate of negative 7.5 pounds per meter. The 7.5 is what we really care about there, because we are losing 7.5 for every meter that we're pulling it up, or 7.5x. So now we have everything we need for our work equation. Work is equal to the integral. We are starting at position 0 and we're pulling it to position 20. Notice that if I had instead called the starting position 20, thinking about 20 feet of line being let out, I would have had to have switched this integral around. But my initial position was 0. That's what we saw here. So it does matter what we're calling the initial and terminal position when we're finding that slope. We better represent that inside the integral as well. Initial position 0, terminal position was 20. Our force equation was 150 minus 7.5x, and then it is changing at a rate of dx as we pull that thing up. So let's go ahead and integrate this. 150x minus 7.5 over 2, which we have a messy decimal within a fraction, but we'll figure that out in a second. 7.5 over 2x squared, and we're integrating from 0 to 20. 150 times 20 minus 7.5 over 2 times 20 squared minus, well, we'd have 150 times 0 minus 7.5 over 2 times 0. That's just all going to zero out. So 20 times 150, 30, add the 2 zeros behind it, minus 7.5 over 2. 20 squared is going to be 400. Half of that is 200. So we'll have 3,000 minus 7.5 doubled would be 15. Add our 2 zeros behind. We get 1,500. Now notice here we can't call it joules. And I did this semi-intentionally. I thought about changing it for half a second. I thought I'll leave it. We had a weight of pounds, or we had a force of pounds. And so I can't call this Newton meters, it's pound meters. And so this means I cannot write this with the joule notation. We can only write Newton meters using that pound notation. And so we get 1,500 pounds times meters, pound meters. All right, let's talk about another example of how we can apply work. Let me copy this definition down. So another good application of changing forces are springs. If you think about a spring and you try to compress that spring in, you push it inwards. The first little bit you're going to be able to push very easily. And then as that spring gets closer and closer together, it gets harder and harder to push because it gets more and more tension the closer and closer away from its natural, or I should say the further away from its natural position. Same idea as if you took that spring, it was just sitting on a table, you picked it up and you pulled it out. First little bit pulls very easily and it's harder and harder to pull it out because the further you get from the spring's natural position, it is more and more challenging to pull out. So we need to talk about Hooke's law. Hooke's law states that the force required to hold a stretched or compressed spring x units from its natural position is proportional to x. That is, we can say F is equal to kx, where this k is the force constant or the spring force. It is that natural amount that the spring wants to retain its original structure, but as we pull it, it becomes harder and harder, or as we push it in, or as we compress it, it becomes harder and harder to compress inwards. So let's take an example of this. We're using same ideas with work, but now we have a new force equation to relate this to as well. So here, an example. A spring has a natural length of 10 inches. And what we mean here by natural length and natural position, that is if you were not putting any force on that spring. If that spring was just sitting in a room, not being manipulated in any way, what would it look like? And then from there we can compress it in or we can stretch it out. So we have a spring with natural length 10 inches, an 800-pound force stretches the spring to 14 inches. We're going to do a few things here. The first thing we're going to do, first thing we always have to do, is find the force constant. Find the force constant. It does not matter if you are applying an 800-pound force or a 20-pound force. That spring's K is going to be the same. We have to find it. We're never going to know what that is. Springs don't come advertised with, hey, the force constant is 2.6. That is something that we have to find based on some measurements that we take. So let's start there. What we know is that an 800-pound force is equal to K times, and if we think about the amount of change here, it's stretched to a length of 14, its natural length was 10. So we're not going to say that its x is 14. Remember, the x is the change in that length. From its natural length to where it ends up, that is that x. So 800 pounds of force get us 4 units of change. And so if we divide the k by 4, we get k to be equal to 200. So now we have that spring constant. We can use that for this spring no matter how many different parts to this problem that there are. That will always stay the same just for this one spring. How much work is done in stretching a spring from 10 inches to 12 inches? So here is where we're actually looking at work. We have a force equation. We know that force, based on that K we found just a second ago, force is equal to 200x. We are going from 10 to 12. So that is a initial position of 0 because its typical stretch, its natural position is 0. If we didn't move from 0, no work would be done. To a stretch position of 12, which means we've gone 2 units. We're going from natural position to 2 units away. I should also note it doesn't matter if we're to stretch it or compress it, those two. Springs work done in both the stretch and the compressed directions works the same. So we're going from 0 to 2, and then our equation that we saw just a second ago, 200x. That is our force for this spring, dx. So if we take our antiderivative, we would get 100x squared. We're integrating from 0 to 2. 100 times 2 squared minus 0 squared. And 2 squared is 4 times 100 is 400. We need to have our units on this. And just like with the previous problem, even though I set this lesson up to talk about joules, I haven't actually given you a problem where we can use joules yet because our force was in terms of pounds and our measure was in terms of inches, so pound inches in this case. Let's do one final part with this. How far beyond its natural length will a 16 1,600-pound force stretch the spring. All right, so here's a case where, again, we aren't even using work. It's the same as part A. So work is another formula we've mixed in, but we need to make sure that we're comfortable with, am I looking for forces? Am I looking for work? What am I looking for? So here, this is the 1,600-pound force. We've already found our K to be the 200. We want to know how far that will stretch the spring. We are looking for the X in this equation. And so when we divide our 200 over, we get X to be 8. And our units were inches, 8 inches. And that's all there is to it. Now from here, could we figure out how much work we did? Absolutely. We do the same integration as before. So we need to just be always aware of what equation we're dealing with when we're dealing with these springs. Am I looking at a force? Am I looking at work? Work, I'm integrating. Force is just a simple proportionality, K times the distance stretched. Make sure that you are not using the lengths. Make sure that you're thinking of the x's as how far it's gone. So this would be a length of 18. The spring length at this point would be 18 because remember it had that starting amount. Just double checking myself, yeah, of 10. And so we want to make sure that we're differentiating a length from how far we've stretched. But work, a very simple calculation. The hardest part is just sometimes finding that formula for our force. And so we have to think about, is it constant? Most problems in this course are not going to be constant. Are we increasing? Are we decreasing? By how much? How often are we decreasing that amount?